Welcome to the first lecture about uncertainty analysis. In this lecture, I'm going to be talking about, it's going to be a kind of introduction. I'm going to be talking about the difference between precision and accuracy, and also the difference between systematic and random errors. So let me share my screen. Okay, so let's start. So what is the difference between accuracy and precision, which I guess has been a topic in a couple of different laboratory courses. And you are going to see that this accuracy and precision, the brothers and sisters of these concepts, are systematic error and also random error. So I'm going to start with an example or a kind of an hypothetical experiment so that we can kind of visualize what's going on and also make the concepts a little bit more concrete. So here is the experiment. Let's say that every day I conduct, so there is water flowing here, let's say. I have a graduated cylinder and there is actually a certain level here shown with a pen or pencil on this graduated cylinder. I fill this to that certain point, right? And then I take this and carry this graduate cylinder filled with water, tap water, let's say, and I weigh it using this balance, electronic balance, and I read this value and record it here. And tomorrow I do this experiment again. Again, I fill it to that specified level. That level never changes. It's specified on the graduate cylinder, and I do that another times, and I record it. I record all these different things. Why I do that is another story. But let's say that, assume that I conduct this experiment in this way. Let me get rid of this part. So the question, or what I'm going to end up with, is a set of measurements. I'm going to call this set X, and each of these measurements will be X1, X2 to Xn, where n is the total number of measurements, and this X is the set of all measurements. And generally, although I try to do my best to conduct the experiment in identical fashion, using the same tap water, using the same graduate cylinder, same weighting equipment, everything is identical here. X1, X is equal to X2 to Xn will not be satisfied. Depending on the number of significant figures that we see here on this electronic device, we are going to usually be seeing different values. And sometimes these differences may be a little bit more drastic compared to the rest of the values. So the question here is, why do we have that observation? This is mainly due to the so-called random errors. It's not going to be the only reason, or it's going to be for the time being. Let's just concentrate on this concept, random errors here. Let's assume that this is only due to random errors, which perturb the real values here. So what do I mean by that? It is better to try to explain this on a simple statistical model. So if you, for those who have taken statistics or probability course, I try to model the universe around, or I try to model what we see outside on an equation here. And once I model the system, the universe using this equation, then I'm going to try to analyze this equation, so that when I analyze this equation, I'll be actually analyzing the universe. So this is why we model the system. So here is how we can model the system. Our measured value, and here I'm going to be using subscript m to show xm as this measured value. And for the ith experiment, I'm going to use in parentheses I. This is going to be the first, second, nth experiment, is going to be equal to the true value here. And here, for the specifics of the experiment, I'm going to talking about the mass or weight of this liquid, or let's make it much more concrete, mass of water here. Since we are always conducting this experiment on Earth, I use the word mass and weight interchangeably. So the true value of this liquid water here inside, whatever that value here, plus some random error term. That's where random error concept comes from for the ith experiment. So the measured value here, the measure that I read here, will indeed be equal to the true value plus some random error term here. Let's make it a little bit more detailed. Let's call this true value as the value of liquid water, which is supposed to fill from this point, from the bottom to the top of this line here, which is supposed to fill this region exactly. Let's call this true value as the mass of water which fills this region. Yeah, you should realize that when I make the definition in this way, any water level exceeding or just below this level is going to reveal itself as the random error term, or the random error term will contribute to this system. Or one of the ways of contribution of the random error terms may be a change of this level, whether it's going to be slightly or up or down. But even if this were exactly whatever that means on this level, the liquid level, still when you put this on this graduate cylinder on the weighting device or the electronic balance, still, for instance, if you put here or put this a little bit on the left hand side or on the right hand side, there may be fluctuations or there may be some effect due to the construction of this electronic device, which may change the value that you read here. There may be some external conditions like vibrations outside or the temperature, which may affect again this reading. So all of these will be buried inside the random error term. The important point here, so there may be other causes of the random error term, or you may not, it's not possible always to assign a cause to a random error term. The important thing about the random error term is it is usually from different directions. So and it changes from experiment to experiment. You may think about like this: if you are, for instance, considering the random effect of where I put my graduate cylinder on this balance, or then the electronic device is going to reveal a different result, kind of thing. Then, so from a bird's eye point of view, this is our top view of our balance. Once I put it here, let's say, the second time I may put it a little bit to the right. Next time it's going to be a little bit left. Of course, I'm going to exaggerating, so it's going to be maybe a little bit like this. So I'm going to be putting in different places, but it's going to be in, since it's random, in the long run, it may be in positive or a negative direction. So each time I perform the experiment, it's going to be in different directions. This is the nature of random error terms. And like if I put a little bit more water or less water compared to this line, today when I conduct the experiment, it's going to be maybe a little bit higher. When I conduct the experiment tomorrow, it's going to be a little bit lower, and it's like that. So it's going to be from different directions, and it's going to change from experiment to experiment. So this is the nature of the random error term. It's going to change from experiment to experiment. Where is the true value? Let me talk about that true value. For instance, you may easily ask, how do we know what the true value is? Here's the interesting thing: we cannot. This is the ontic, from a philosophical point of view, this is the ontic property of the matter of the outside world. We assume that there is a true value of water which fills this region here, and it's going to have a certain mass or weight, which is going to be a true value. But in reality, the best that we can come up is the measured value. So for instance, in this experiment, how can we reduce these random errors? As I'm going to mention below, one thing to do is try to locate where these random errors may be affected, what may be the causes of root causes of these random errors which contribute to variation in the system. For instance, here I said the location of where you put your graduate cylinder on the top of the weighting device, or the balance may be one cause. So you may always put your container on the same spot. There may be one way of dealing with this random error. This is going to decrease the variance of random error. I'm going to come to a minute. What do I mean by variance of random error? Or you may be much more careful about coinciding this level here with the line here with the level of water. This is going to probably decrease the random error terms. But however whatever you do, there's going to be usually a random error term usually remaining there, which is going to cause deviation from experiment to experiment. But the best that you can do is by carefully examining the experimental procedure, you can decrease the random error terms. But there is another statistical method here, and which I'm sure we intuitively know that, which is called averaging. If we repeat the experiment, we intuitively realize, or maybe without going into those error things, but just repeat the experiment and take the average values, we seem to understand that this is a better procedure for decreasing the errors or for obtaining better results, whatever that better means, which I'm going to come in a minute. And that better is going to correspond to word precise, by the way. So let's talk about, or let's justify this intuition or heuristics in terms of statistics. When we repeat the experiment, let's go back to our model. So we are now living in the model world, and we are trying to understand what's going on. The first measurement, for instance, is going to be equal to the true value plus an error term here at 1 here, 1, the first experiment. The second measured value, xm2, is going to be, note that still is going to be the same true value because I aim for the very same experiment, the same level here. But it's going to be a different random error term, blah, blah, and I conduct this experiment, let's say, for n number of times, right? The number of times I conduct the experiments is n. So they are going to be n different random error terms. If I add them all together and divide by n, these n will cancel here. I'm going to be obtaining average measured values. Note that these are the values that I obtain. In real life, I won't be knowing these and these. And the errors will be also measured. The random error terms will be measured. Well, okay, when I obtain this equation, it doesn't seem to be very much helpful because I neither know the true value, neither know the individual, nor the average of the error terms. So now let's study the statistical properties of this equation and also this equation. Why these two equations? Because this is the equation representing a single experiment. This is the statistical model or equation representing the result of the n average experiments. So the first thing that we do, I'm going to do take the expectation of both sides using the expected operator to see what's going on. And we are going to probably remember a couple of concepts from statistics class. So when I take the expectation, when I apply the expectation operator, let me use it here, apply the expectation operator here, and apply the expectation operator here. Since this is an addition here, an expectation operator is a linear operator, we can apply expectation here and here separately. So therefore, when we do that, here we are going to be obtaining this result here. And since xt is actually a statistical quantity, it is a population parameter in terms of statistics. It is a constant. Therefore, it doesn't have an expectation value. It is what it is. So this is going to be itself the true value. Expectation of our single experiment, therefore, is going to be equal to the true value plus expectation of the random error terms. So now here's the question. What's the expected value of random error terms? Well, since we haven't modeled what the random error is yet, we have talked about it briefly, but we haven't come to a clear or concrete understanding or with a concrete model of random error. Let's come up with that right now. Random error usually assumed to be of zero mean. And the reasoning is because of the nature of the random error. If you remember, I tried to characterize random error acting in different directions from experiment to experiment. So in the long run, we assume that if you sum all these random errors, since they are going to go in different directions, they are going to cancel each other and it's going to go to zero. Therefore, statistically, random error is distributed around zero mean. And usually we go one step further. We assume that it is symmetric distributed, and it is due to the very same reasoning. If you go from left and right side with equally likelihood, then it's going to be symmetric distributed. And we have a very nice distribution for that, normal distribution. So this is actually a definition or an assumption that we can use to model the random error. It doesn't need to be always like this. In different cases, there may be different distributions of random error, but usually we define random, we characterize random error with normal distribution, zero mean, but with a certain variance. Now, what's that variance, or where does it come to? It depends on the imprecision related with the experiment I tried to talk about before. For instance, if you perform the experiment not carefully, if I do not that much care about whether I exceed that line or whether I am below that line on the graduate cylinder for which we're going to fill the water up to that point, right, then that variance is going to be higher. If every time I put the on the balance the graduate cylinder in a different location, then the variance is going to be higher. So if you are careful about the experiment, then this variance is going to be smaller. Anyway, so let's go back to our analysis here. Expectation of xm, we said that is equal to xt plus expectation of a random error. Since this is zero, our expected value here, this is an important result, our expected value of a single experiment is indeed equal to true value. And if I apply the same analysis for the second model, use expectation operator on both sides, note that this is going to be still xt, and this time it's going to be expected value of an average of random error terms. Since each random error term is going to have an expectation of zero, therefore this expected value of the average of our experiments is still going to be equal to the true value. So when it comes to the expectation, or what we call bias analysis, if you recall from statistics, both of the procedures, a single experiment and averaging from multiple experiments, has the same advantage, or they are equivalent to each other, because for both cases they are unbiased estimators. So what is the advantage of this averaging, and what's that got to do with random errors? It is this: if I apply variance operator for both sides this time, instead of expectation, I apply variance operator. And when I do that, and if you go back, variance operator for independent quantities, note that variance of xt, first of all, okay, independent quantities next is going to be xt is constant, right? So variance is going to be equal to zero. Variance of our measurements is going to be simply equal to variance of our random errors for a single experiment. Whatever the random error variances, they are directly reflected in our measurements. On the other hand, if you take averaging, variance of xm bar is going to be equal to variance of summation of these random errors divided by n. Here, this is where we use the independence property of random errors, and this is another assumption. When it comes to random errors, we assume that each experiment is independent from another one. This seems to be a very reasonable assumption, but please pay attention to that. It may be a little bit deceiving. For instance, if you do this experiment, let's say in a single evening, you do this experiment 3 times in series, and you feel very tired on that evening. In this case, being tired is a random effect, right? On another day, you may feel very differently, very good or very ill, it may be healthy. All these things, the states may refer to these random error terms. But when you conduct the experiment 3 times series in a certain state, then these 3 experiments will not be independent from each other, and the random error terms will not be, due to our health state, will not be independent from each other. So be careful not to violate this assumption. So if this assumption is accepted, then in this case, covariance of EI and EI plus J for every J term which Ji is not equal to I is going to be equal to 0, which practically means covariance of, for instance, E1 and E2 is equal to 0, or E3 is equal to 0. So why this J is not equal to I? Because when you put 1 here, covariance of E1 and E1 is actually equal to variance term, and it is of course non-zero, as I tried to explain. Anyway, when you do that, variance of our average measurements is going to be equal to sigma square over n. And actually, for those who remember from statistics course, that is the power of averaging. It decreases the variance term, and this is exactly what it does. So basically, what we have here is variance in the measured value has decreased by a factor of 1 over n. What do I mean by this? Variance of a single experiment is sigma square. Variance from an average of multiple experiments conducted for n times is equal to sigma square over n. So as n increases, you decrease the effect of random error by decreasing the variance term. So so what does it mean? The resulting xm bar value is likely to be closer to the true value. Why? It is because of this. If you go back to this equation here, since the variance of this term is small, you may easily assume that, and since we assume that this is normal distributed and this is a parameter value constant, xm and xm bar is going to be normal distributed, and this distribution is going to be pretty much narrow around the xt value, since the variance here is smaller. So what does that mean? It means effect of random error is reduced by repeating the experiment. It means precision of the measurement is increased. Therefore, what we call precision is totally related with the variance of random error terms. In a single table or a frame, variance of random errors, as they are decreased, precision of our measurement increases, or vice versa. Variance of random errors terms increases, precision decreases. So in order to increase our precision, which is one of the aims of our experiment, we usually use repeating. And as I mentioned above, another way to increase precision is to go over the experimental procedure and try to decrease the variation in the experiment wherever that variation stems from. So try to identify the root causes of those variations and try to reduce those variations. So for instance, if this experiment in each day is conducted by another person, it's going to cause an additional variance because each person is going to have a different eye view, right? A different way, different amount of carefulness or carelessness which is carried in the experiment, and therefore in the measurement results. Now comes the second error source. So the question is there any other source of error? Unfortunately, yes. And again, going from an example, let's say that the electronic balance is badly calibrated, so that it weighs less than 1.5 grams than the true value. In this case, there's going to be a bias of minus 1.5 kilograms. I'm going to explain why this is so in a minute. And this is going to be called systematic error. Now, you may easily say that, why do we assume such something like this? Why isn't it perfectly calibrated? And now the problem comes, actually, at least due to the random error terms during the production, the calibration and the construction will never be perfect. Think about the things that you buy, electronic devices, cars, whatever. There are going to be always something problematic, a little bit more, a little bit, or maybe it's in some cases, more serious things are problematic, but there are always some parts which may cause some problems. So whatever you do, there's going to be always some problematic parts. Of course, it's not the same example, but when it comes to this, the weighting machine will not be perfect, right? So it's not going to be random error. So you may easily ask, why don't we put this term or this contribution into random error? Because the important point there is that contribution from errors is going to be constant with respect to experiments. It's not going to change from experiment to experiment. Or another bias maybe, which we are going to call another systematic error. Maybe my eyes, for instance, has got a problem, but it's not a random error. It's not for one time it's going to be higher or lower than the level. When I look at something and I see that two things are on the same level, indeed, what is beneath is a little bit always lower than the one on the front. I'm just making it up. But when I conduct the experiment in this manner, the level that the water is supposed to reach is going to be a little bit higher compared to the actual level, because I'm going to think that that is the level there. And note that in experiments, from experiment to experiment, this may be a little bit higher or lower due to random errors, but due to that constant bias effect that I have inherent in the measuring device, which includes me and the equipment that I conduct the experiment and the procedure, the whole thing is going to carry a constant bias term, which is not going to change from experiment to experiment. So in this case, a better way of modeling the measurement or the experiment is going to be with this equation or with the statistical model here. Very similar compared to the first one. The only difference here is I have added a bias term. So measured, the final measurement is going to be the true value, which is not going to change from experiment to experiment. Bias, which is not going to change from experiment to experiment, and the random error term, which is going to change from experiment to experiment. So this part is the random error term. This part is going to be systematic error. So when I take the expected value of both sides, note that I get rid of this error term. This time experimental measurement is going to be equal to true value plus bias. So when I take xt and put on the left hand side, I come up with the definition of the bias term, again for those who can remember from statistics course. It is the expected value of my measurements minus the true value. If this is 0, my measurements are symmetric around the true value. On the other hand, if this is not 0, some positive or negative value, for instance, like this one, that it weighs less than 1.5 kilograms. So this is the true value. This is I expect this value to be less than this true value by 1.5 grams. Therefore, the bias is going to be 1.5. Now, what about the variance? We may say, can't we do the averaging thing here and get rid of bias here? Unfortunately, no, because if I do the very same thing here, I repeat the experiment. This time, I show this repetition experiment with my new model, with my upgraded model, I may say. I add the bias term here, I add these values and divide by n averaging. Then the average value is going to be equal to true value plus bias plus variance term. That's great. Now, variance of x bar is still equal to sigma square over n. Therefore, averaging has actually worked again for this case, and we decrease the random error terms. But note that there is nothing related with bias here. And the expected value of x bar is equal to x true value plus bias. So when it comes to, if there is a bias term, averaging does not affect the bias term. You cannot decrease the contribution of the bias term to the X bar value, to the measured value here, and you cannot decrease the effect of bias in the variance terms. So averaging doesn't work if there is a bias, but still we do averaging in our experiments, right? And try to be careful about sources of random error, but bias is another story. So bias is related to so-called accuracy. So this is the difference between precision and accuracy. If you look from that perspective, they are totally unrelated. The only relation is they both stem from the concept of errors. But when they are random errors, it's related to precision. When they are related with fixed errors, systematic errors, then accuracy as systematic error is small, which means bias small, accuracy is higher. So the question may be, how can I increase the accuracy? Now, this is a bit more difficult question because this bias is in the unmeasured part. Of course, the random error were also in the unmeasured part, but I can hypothetically decrease the variance just using the averaging. This part is totally the unseen part, true value and the bias. So I do not know indeed the bias value, and it's not possible to know this. One way to deal with the bias term is to look in the procedure to or to search for in the procedure or parts which may cause biases. Of course, this is pretty much meaningless. Let me try to go in this experiment again. When it comes to this experiment, for instance, if during this procedure, let me try to get the bit of these as much as I can. Let's say that I fill the graduate cylinder up to a point, right? Then I bring this graduate cylinder to, okay, it's pretty good. To this weighting device, and I put it here. I measure the weight. That's okay. But let's say that there's a long distance between the location where I fill my graduate cylinder with tap water and bring it to the weighting equipment. And during this, let's say, transportation, I spill some of this water sometimes. Now, can I call this random error? Indeed, no. And a little bit, yes, but I'm going to talk about why there is also the no part. Note that random error is you assume to be symmetric in two directions. So this is not like I'm, if the whole thing was, okay, I changed the experiment. If this is all in a rainy day, and for some reason I conduct this experiment outside, so in this rainy day, I fill this with tap water, and while during this transportation, I spill some water outside, and rain water also falls in the graduate cylinder, and I put it in the weighting equipment, and I measure the weight. If this were the experiment, this rain falling and my spilling water might, not exactly, but might cancel each other. So we may call these two effects as a kind of random error. But note that there is no rain, so it's going to always, this transportation will always decrease some water. The average amount of water spilled due to this transportation will be the bias term. The average amount. Why do I call it average amount? Because each time I transport this, there's going to be different amount of spilling. Sometimes none, sometimes a little bit more, sometimes a little bit more. So around that value, bias value, there's going to be also a random error term, depending on the experiment. So this is going to be the total volume of water spilled here. There's going to be a bias, and there's going to be a random error term around that bias. Random error term is not very important. As I said, you might be much more careful, or you might be, I don't know, you may use averaging. But when it comes to bias, it means you are going to spill some amount of water, this means there's going to be less water than is supposed to be here. So you may identify this. Of course, this is a very straightforward and not a very interesting and intelligent way of experimenting. But what I would suggest is, of course, instead of that transportation, bring this weighting equipment here wherever you put your or you fill your water with tap water. A very simple solution. So like this, try to identify biases. Most of the source of bias are related with the equipment. Here, this bias was related with the procedure. What do I mean by the equipment? For instance, this graduated cylinder and this weighting device, they are manufactured. And the manufacturing, I'm going to be talking more about this in the second part of the lecture. But during this manufacturing, due to random errors or maybe the biases themselves, this graduated cylinder and the weighting device will not be perfectly accurate. So there's going to be some bias terms related with those volume measurements and also mass measurements or weight measurements, because the devices themselves are going to be biased. So using better equipment, right, more accurate equipment is a way to get rid of or to decrease the bias terms and to increase the accuracy. Or if you are conducted this experiment under sun, let's say, then water will evaporate. There's going to be another negative bias, blah, blah, blah. But I think you get the idea here. So the most important distinction between those two, both of these terms, systematic and random errors, distort or perturb the true values, so that the resulting measured value is going to be both imprecise and inaccurate. But you may, using some techniques like averaging and also search for the sources of these error terms, you may, and then, of course, trying to reduce or trying to get rid of these sources or correct the equipment and the experimental procedure, you may come up with a more precise and more accurate measurement. Now, the overall picture here is, again, let me go a little bit further with statistics. Actually, each of our experiment X measured, this time I wrote it as Xi, is going to be going to be a Gaussian distribution around an expected value of X here. Here, for instance, expected value of X, each measurement is going to be like this. So why do we have different values here? It is because of the imprecision, because of random errors. So this bell shape is totally related with random errors. On the other hand, the difference between expected value here and the true value, which we do not know, is totally related with bias. It's not related with the with random error terms. When you repeat the experiment again and again, what you do is you narrow down this distribution again around the expected value of X. On the other hand, the bias term still remains. If you want to eliminate bias term, as I said, you should go back to your experimental procedure and change something structural. So accuracy is basically 1 over bias, is proportional to 1 over bias, right? And it is actually the distance between the expected value of X and true value here. As I said, precision is related to, okay, this should be variance. Precision is proportional to 1 over variance of X terms. So, and this is actually equal to width of the distribution of the measurement. So the smaller is the width, the more precise are your experiments. Okay, I think this is pretty much clear, but this is a very, very standard or conventional representation of accuracy and precision. So I would like to also talk about that very briefly. In archery, for instance, let's say that this is where you are supposed to hit, and these are the results. When you improve your eye vision, for instance, we can decrease the variance of random errors. Actually, improve the eye vision is not a very I don't think it's a very good explanation. Actually, I'm not familiar with archery much. Not much. I'm not familiar at all. But if let's say that this scattering, there are, as you can see, there are two problems here. There is a large area which is scattered, and the large area here, the center of mass of this or this location of this large area or the sample is pretty much distant to the point where you aim. So this is both inaccurate and imprecise. So if you somehow decrease the variance of random errors, and this may be, let's say that you do not aim too carefully, you just throw it, right? So if you improve that, you become much more careful, then your aiming is going to be better, or sorry, the positions that you hit is going to be scanning or spanning a narrower range. Now precision has increased, but still, as you can see, the accuracy is bad. This may be due to the position of the ball, or maybe something wrong with my eye. So if, for instance, I change only the position of the ball, I a little bit pull it downwards, then this is going to be the result. Note that this result is accuracy high, but precision is low. So we can have a fourth option here. If we apply both of these, change the position of the ball and improve the eye vision, right? In this case, this 0 point here, the aim is going to be, most of the points will be scattered around in this region. So therefore, the center of mass will align with the aim. Therefore, it's going to be an accurate measurement or accurate result. And also the results will span a smaller area, which means precision is going to be high. So that's very conventional or traditional way of explaining the difference between, or the relation between, accuracy and precision. This is correct, but with respect to our experiments, I think the first explanation was a little bit more friendly or useful, but you may take any explanation that you like. Now, one last note. We have also called something called blunder. These are usually associated with outliers in statistics. The very simple example, let's go back to our example again. During carrying water, after collecting from tap water to our weighting device, we skipped, right? And this has fallen down half of the water or all of the water with the graduate cylinder has cracked and all the water has gone, spilled. Now, am I going to write 0 kilograms here when it comes to weighting, because no water is left? So it's going to be, let's say, 2.3 kilograms, let's say 3.8 kilograms. Of course, that much difference is a bit unrealistic. And another measurement, one day it's 0 kilograms. Now, and you are going to say that, okay, this is a random error or probably a systematic error, but because I spilled and I skipped and spilled all the water. No, it is neither of them. It is neither. Well, it looks like a bias, but this is actually what we call blunder, because this is a violation of the experimental procedure. As I tried to mention before, both bias terms and the systematic error terms and also the random error terms are in the nature, are within the structure of the experiment. You can change a couple of things in the experiment and make them better, but that's another story. This step, if you behave according to if you misbehave with respect to an experimental procedure step, then it means that experiment is not conducted. Therefore, the result is not going to be it's not going to be a reasonable result that one should consider. You should not include that result. if you include that result, it's going to be usually deemed to be an outlier. But that's a little bit of a tricky point. It doesn't mean that every outlier is due to blunders. So be careful with that. So the resulting error is going to be neither systematic error nor random error. So in your experiment, if there are some parts which are not conducted with respect to specification and you realize that, if you do not realize that, that's another story. Maybe you missed some part or you think that you have behaved correctly, but actually the whole procedure was incorrect. That's another story. That is possible, and this may be random error, or this may be a bias if you do it successively for different times due to some other reason. Maybe it's the part which you have misread, which is very easy to skip. But anyway, if you have realized that you have done something wrong, then even if you include that result in your data, in your raw data, do not include it in your calculations, right? And say that this result is due to a blunder, a gross error, you may also say.